Bom dia. Good morning. First of all, I would like to thank the Portugal Air Summit to have invited me in particular, and also it's an honor for the Portuguese Air Force to be involved in this exercise, which we believe it's becoming more and more relevant for the region, but also for Portugal and for those that have been involved. I would like also to thank the participants of this panel, Dr. George Nikolakopoulos from Sweden, Dr. Roger Groves from Holland, and Chris Collot from the United States of America. Also, a thank for the audience that we have here. I'm sure that the audience, like everybody now, is experiencing a different environment as the result of the global turmoil that we have been experiencing since the last month. This exercise, it's a 40 minutes exercise. We will have presentations from these three persons that I have mentioned, and the remaining time will be available for queries that I myself will raise. Should the pace be faster than expected, we will move on into the next participant. With regard to the subject that we have now to approach, we are talking about robotics in the maintenance, repair, and overhaul. Now, this is, up to a certain extent, a new issue. It's a new technology that have been progressively installed in the aeronautical environment. It's not new, but it has a long way still to progress for various reasons. Due to the complexity, due to the regulations, due to the safety, due to the complexity of the process itself. Anyhow, the industry and the academia, they have been working together, and the next three presentations, discussions that we will see are examples. Up to a certain extent, the status of the art of this discussion, and I am sure that at the end of the day, we will be more informed of this aspect, that it will be more and more utilized by the organizations. As we all know, all types of aircraft, regardless of the size, they have to be stopped, grounded for a certain time, mainly for schedule inspections, if not for other reasons. And in that respect, one of the activities that we have to perform, it's the inspection itself. The inspection, it's time-consuming, it's very much depending on techniques, it's very much depending on people, and the utilization of robotics could be a drone, could be a different type of, let's say, of equipment. It's now becoming more and more utilized. In this respect, we will have then three presentations. We will start the presentation by Dr. Roger Groves from Holland, and now we'll make a brief presentation of Dr. Roger. I need to read because it's extensive. Professor Roger Groves is an associate professor in the Aerospace Non-Destructive Testing and Structural Health Monitoring at the Delft University in Holland. He has a PhD in optical instrumentation from Cranfield University, and he previously worked at the University of Stuttgart before joining the Delft University. He leads the Aerospace Non-Destructive Testing Research Group. He's also research in various domains, and his main goals of activity involve automation of non-destructive testing and composite manufacturing, and also sensing and decision-making for smart, efficient aircraft maintenance. The stage is yours, Dr. Roger Groves. Thank you.
Okay, thank you. I'm just just sharing my screen. So just to check everyone can see the slides. Okay. So good morning, everyone. Good morning, everyone. So I'm Roger Groves, Associate Professor in Aerospace NDT SHM at TU Delft. Today, the title for the presentation is Enabling Automated Inspection with Artificial Intelligence. And the aim of this presentation is just to give you an introduction to some different aspects of how sensors, robotics, and artificial intelligence come together for MRO. So the Aerospace NDT Laboratory at TU Delft. We work on the topics that were mentioned, automation of NDT and sensing and decision making for aircraft maintenance. And I'd just like to also add that we work on education in these topics as well, in sensors, inspection, and monitoring techniques, and in artificial intelligence. There are three main topics in my research laboratory. Optical metrology, which is camera-based sensors. I'm showing here example, left-hand picture is of a 3D chirography instrument. We work on ultrasonics, which is the right-hand picture. This example shows air-coupled ultrasonics. And we also work with fiber optic sensing. And I'll show you a picture here in the center, which you can see the fiber optics, but they're being used for the monitoring of a composite hydrogen tank during testing. And they're buried behind the ice layer that you can see on the hydrogen tank. So hydrogen, I think that connects to the topic of sustainability that's already been mentioned this morning. So what are we actually doing? How are we connecting up with using robots for inspection? This slide just shows about robot-enabled inspection. We worked on a project on inspection and automated repair of curved CFRP panels. This is a defense technology project in the Netherlands, and we work with the Royal Netherlands Air Force. On the left-hand side of the screen, you can see that we have the robot, the test panel that we worked on, and you can probably see that there's a laser sensor, laser line scan sensor, and we use that sensor to scan over the panel initially to get the geometry, but then we also introduced artificial impact damage. We were able then with this sensor plus machine learning algorithms to identify the size of the defect, to automatically identify the area which needs to be cut out for repair. And then on the right-hand side, this is a portable 5-axis milling machine.
Dr. Groves, are you listening to me?
Yes.
We don't see anything on the screen.
Oh,
We have two persons, strangers, but not exactly the things that we were supposed to see. So you need to check what is the what's going on. We'll wait. We have time. Don't worry. This isn't a flight issue.
Yes, I'm back now. Let me just try again.
Yes, please.
I can share my screen. Can you see it now?
Not yet.
So it's beginning with the presentation.
Take your time.
Yes.
We still have half an hour. Good.
Yeah.
Good.
Yeah.
Can you go back to the first slide, please, so that we can make it coherent with your speech? Is that possible?
Yes.
Okay,
yes.
Thank you. Sorry for interrupting you.
Are the slides visible now?
Yes, perfect.
Okay.
Thank you.
And still now?
Yes, you are not seeing,
Okay.
but what is relevant is the presentation.
Okay, thank you.
Perfect.
So yeah, I gave my introduction. I wanted to just quickly show you these 3 examples of research topic areas in my laboratory. 3D chirography, which is the left-hand picture. Fibre Bragg grating monitoring of a composite hydrogen tank during testing in the middle picture, and an example of air-coupled ultrasound in the right-hand picture. Let me go on to where we're using robots for robot-enabled inspection. These are examples from the Defence Technology Project. We can see here in this picture the test panel. We're scanning the test panel with a laser line scan sensor. We're analyzing that data to determine the curvature, the extent of damage due to impact on the panel. And then on the right-hand side, we have a 5-axis milling machine, which has been also a portable one, which has been placed on the panel and used to mill out the repair patch area. Of course, we then, in this project, we then added a repair patch. It was bonded into the structure, and then we repeated the non-destructive inspection analysis to confirm that the repair had been made satisfactorily. So this is a technique to speed up and automate the repair of composite aircraft. Okay, the next slide I take a little bit of direction away from maintenance and just give you one example from aircraft manufacturing. In the aircraft manufacturing, in the automated fibre placement process, there are a number of different defects that can be introduced. The picture in the top left shows some examples: wrinkle, twist, gaps, overlap, and foreign matter that can be found. Of course, later we like to find them in the manufacturing so that they don't become a problem during in-service. In this project, we worked with also with a laser line scan sensor fitted to a robot. This was a collaboration with a DLR in Germany. And it's been mentioned briefly before this morning, but one of the very important things with using artificial intelligence to inspect product or parts that are in service is to look very carefully at the false positives rate and the false negatives rate, and to work very hard on the reliability of the algorithms to give you a correct diagnosis of the part that's being investigated. Okay, I'd like to just show one nice example here. This is inspection of tires. This is during tire qualification tests, which are performed with Airbus. We use the tire test inspection. I guess we should call it tire truck, which can actually, you can fit one aircraft tire in the center, and you can apply a force to the ground and a different rotation of the tire to perform, to check the wear on the tire. Left-hand side shows an early picture from the project where I had the idea to place the bicycle wheel onto the robot that we have in the laboratory in TU Delft. And in the center lower picture, you can see the sensor that we've placed close to the tire. It's actually in a sort of a hostile environment there with pieces of rubber and smoke and a difficult environment. In this test, we were able to see that the tire degradation was of the order of 10 millimeters, and we saw some variations in the tire degradation depending on the loading that was applied to the tire. Okay, and now we'll come on to well, just to briefly introduce a new project that we're starting in the Aerospace NDT laboratory. This is drone-enabled inspection. The project is called AirTub, automated inspection and repair of an offshore turbine blade in a wind park. Wind park is in Borssele 1 and 2 wind park in the North Sea, off the coast of the Netherlands. And in this project, I don't have any results to show yet, but we're developing miniaturized inspection technology to be carried by the drone to perform automated NDT inspection offshore. And of course, the things that we learn in this project will not only help to improve the sustainability of the energy supply, but will also find their way back to the aerospace environment for aircraft inspection. And then my last technical slide is I wanted to just show the one of the competing techniques for the robot inspection. It's also been mentioned before this morning, which is structural health monitoring. So in my work in structural health monitoring, one of the main aspects I look at is the design of structural health monitoring systems for real structures, and also the positioning of sensors to cope with different types of damage. So deterministic damage is damage that occurs where there's a high stress concentration in the material, and probabilistic damage, this is damage that occurs, for example, due to random impact damage. In this project, we tested with a number of artificial intelligence methods. One that I can just briefly show here is the genetic algorithms, where we take a good performing artificial intelligence algorithm in the parent generation. We perform mutations on that to generate mutated children algorithms, and we also perform crossover to generate new algorithms. And in each generation, we test the new algorithms, and the strongest algorithms survive to future generations. And my experience with this technique is that sometimes it's a little bit time-consuming to perform this genetic algorithm development, but it does generate very good final algorithms. And just the picture on the right just shows the positioning for the best and second best position for structural health monitoring sensors. Okay, so with that, I'd like to thank you for your attention and pass it back to the chair of the session. Thank you.
Thank you, Professor Gross, for your presentation. We'll come to that later. Now I would like to give the word to Professor George Nikolakopoulos, for which I make a short presentation. He is chair professor in robotics and artificial intelligence at the Luleå University of Technology in Sweden. His work involves robotics team in the DARPA Grand Challenge with the Jet Propulsion Laboratory NASA work. The Professor George Nikolakopoulos also works and have been working with the robotics team in artificial intelligence at Honda Research Center in Japan, and he has been nominated for various awards during his career. Namely, he has been appointed for the Wallenberg Academy Fellow candidate in Sweden. The stage is yours, Professor George Nikolakopoulos.
Just a short correction. Unfortunately, George Nikolakopoulos had a very urgent meeting with the European Commission that he could not avoid. I'm George Andrikopoulos. The name is really close. I'm a senior researcher in his team, and I'm the technical leader of the projects that I'm going to present to you today.
Thank you.
So I hope that it was okay. We took the liberty of making this swap rather than providing you a recording of the presentation. So I'm going to take over the presentation and the questions, and I think that it's going to cover any questions regarding the technology. I'm going to start sharing. Please inform me if the share, of course, doesn't work. You see my screen?
Yes.
Can you see the presentation or the PowerPoint?
Mm-hmm. Yes.
Okay. So with this presentation, we are going to provide you an overview of our activities regarding the robot means, the robot platforms used for inspection of infrastructure, and in this case, the advances that we have done the past about 4 years in inspection of aeroplanes and infrastructure like wind turbines. So the AirTab project that Professor Groves presented finds us very, very interested, and we're going to present some of our results from that specific, let's say, area. But also inspection of mines. We are working together with one of the largest companies in Sweden, with LKAB, and with Epiroc, with Boliden in mining. And we are trying to automate the process of inspection in those very, very harsh and challenging environments. So I'm part of the Robotics and AI group. I'm Georgios Andrikopoulos. We have been in Sweden for the past about 10 years. The group is newly founded though, and it's very, very fast expanding. As you also mentioned in your presentation, we have been having collaborations with the biggest, let's say, players in industry, in mining and in telecommunications. We have been having also collaborations with Honda on social robotics and with NASA, where we very recently won the DARPA Subterranean Challenge. And we just mentioned it because we are the only team in Europe that actually took part of this in collaboration with JPL, Caltech, MIT, and KAIST. So to the part of this presentation, as part of Project Compinova, which is a Future Emerging Technologies project, an Horizon 2020 project running for the past about 4 years, our goal has been the development of Vortex robotic platforms, so climbing platforms, as an alternative to other applications that we have seen done with UAVs, with drones. And in this case, multiple climbing platforms that can carry different tools and sensors and enable the autonomous operation, the autonomous execution of inspection tasks. In this case, our collaborators, our partners in the project, Cranfield University and Ioannina University in Greece, have been developed the sensors phased array and infrared thermography. So we are talking about contact-based sensors and contactless sensors tested on composite aeroplane structures. So the challenge of the project was to identify the damages and quantify the damages of the composite in the composite materials, but also the challenge of repairing the damages via a semi-automated climbing manipulation system, which is constructed by University of Patras. So today we're going to give you a short presentation of the activities that we have been doing on the Vortex robot platforms, and a couple of videos to that to show you. I don't know whether you can see the videos, because I understand that you don't see the presenter's view. Just a verification, can you see the video? So the climbing robot platform uses the principle that says that when we put an electric ducted fan close to a surface, there is a sweet spot, there is an optimized distance where we get the vortex phenomenon and the maximization of the adhesion force. So we are using this principle in order to produce a platform that can hold a high payload, and in this case it's 7.5 kilos, which gives us also the ability to mount sensors and different tools. We have been testing and evaluating the specific platform in different scenarios, not only onto aircrafts, as you see in the video, which was one of the successful, let's say, trials at Cranfield University on a Boeing 737, where we tested the mechanical properties of the robot and its ability to traverse different surfaces of an aircraft, from a fuselage to wing, and also the challenging transitions between the wing and the fuselage. So from that part, we're talking about the structural challenges of using such systems, and of course, as you mentioned, the challenges of using automated systems in close collaboration with the human operators. Currently, in respect to Compinova, we're performing the final integration tests with the sensors and the final tests on real composite panels in assessing the general efficiency of the solution in handling autonomously again, and we highlight that, autonomously the inspection, but also semi-autonomously the repair via a laser cutting process and a patch placement process performed by an automated system. We have been developing different technologies, and in this case, software integrations and autonomous behavior also for wind turbines and mines, as I mentioned. This is a video of field trials that we did in north of Sweden in a wind park. And in this case, we used drones and optical representation, optical cameras, in order to visually inspect the wind turbine. The visual inspection was done autonomously. We have performed also collaborative path trajectory generation in order to use multiple drones for that particular purpose. And the end goal was to recreate a visual representation, a 3D reconstruction of the wind turbine in order to assess visually any damages on the surface. Of course, a lot of challenges also here, the absence of features, as we are talking about a quite uniformal structure, but this is something that we are currently developing, and we are currently testing not only with the drones, but with our climbing robots. So we are developing algorithms and software in order to account for autonomous inspection, for disturbances like high winds in this case, but also to account for human-robot collaboration in case of airplanes, and in case where we want the robots to work collaboratively with themselves, but also with the human operators. So this would be, let's say, a brief presentation of our efforts and our activities that are funded by Horizon 2020 projects and also our worldwide, let's say, collaboration with the aforementioned companies. So that would be the end of the presentation. Apologies, but there was a mix-up with the multiple screens, so I guess that you were seeing all this time the PowerPoint, but I hope that you got the first, let's say, idea of our activities in the field.
Thank you very much. Now
so
we
much.
move to Christopher Colloy. Christopher Colloy, who is in the United States. I'm sure he should be sleeping today, but still it's the difference in time. I'm making a presentation of him saying that Chris Colloy is a senior manager of the quality and mission success at Lockheed Martin and the architect of the aeronautics quality technology vision. He has been involved in projects to develop aerial drone-based inspection methods that include machine vision and collision avoidance crawler drone-based inspections. He was also featured by Fast Company online magazine as part of the Innovation 360 segment, which focused on Lockheed Martin in 2019. The floor is yours, Chris. Chris?
Good morning. Thank you. Can you please confirm if my charts are visible?
Yes. Perfect. Roger.
Thank you very much, everyone. In the introduction, it was noted that my expertise is in quality. And so today I'd like to talk about how artificial intelligence and new technologies are applicable to the MRO field. And excited to be here. Thank you. So very briefly, of course, these technologies are made possible by Industry 4.0, and in the quality arena, for us, we call this Quality 4.0. And as you can see in the picture on the bottom right, the reason this is so important for us is because the technologies that we use today in our factories and our MRO facilities tends to be human-centric. And so if you picture an aircraft inspection on a component like you see in this picture, the classical technology is a hand and a flashlight. And that, unfortunately, that is what historically, that's what we see today still. Historically, it's been the best method, but I think that there's a better future possible with the newer techniques made possible by Industry 4.0. And I think artificial intelligence is one of those critical roles, as we've been talking about the past 2 days in the Air Summit. So specifically for the MRO arena, you know, the problem associated with doing human-based inspection has to do with one, safety, and two, hidden cost. So anytime that we perform an inspection in a confined space, whether that be inside of a fuel tank, which of course has odors and has to be vented first, there's a large cost in terms of prepping that bay for a human to enter. And you would have to think that there's got to be a better way to do this, as well as climbing on top of a large aircraft and doing an elevated space inspection. So it's interesting in our research, we've kind of uncovered that you know, that the time it takes to do the inspection is one thing, but the total time involved with setting that inspection up with the safety spotters, the personal protective equipment and procedure can actually raise the cost of these inspections by 4 to 6x the HPU associated with just doing the inspection if you were standing on your own 2 feet. So that makes a huge use case for investing in these technologies for the betterment of our process. Now, most of us who have classically been in this environment are very used to you know, gauges, and by training our operators to minimize that measurement variation. What we're going to see is that you know, we need to be more focused on AI, and that of course induces some new areas of concern. One of them is, how do you validate and qualify those AIs? And this introduces a data science body of knowledge that's a new emerging topic for everyone in the arena. And also, how do we qualify that the AI is performing the work correctly? So much like how you would qualify a gauge, there has to be this process in the future of qualifying the AI as well. So comfort on both sides of the spectrum with the traditional gauges and with the new AI is a real challenge for all of our human capital systems, and something that we all need to be paying attention to. So as an example of what is possible when you incorporate artificial intelligence and robotics in an MRO environment, I'd like to offer an example that was made possible on one of our airship programs for the process of doing pinhole inspection. And on the bottom left, you can see you know, what has historically been the classical process, where you would take a very bright light and you would shine it at the airship. You'd have to partially inflate the airship because someone would have to go inside and look to see if there was a beam of light coming through pinholes. And so, again, just doing that inspection already takes 2 people, one person to hold the light and one person to be on the inside. But of course, you notice there's other people in the field of view, and these are the safety spotters and the other equipment handlers to make this possible. So already, this is a 4-person job, and it could be done so differently nowadays. So if you were to have you know, a drone that would adhere to the outside of the surface, that could perform in a swarmed activity with other drones, you could rapidly scan the envelope in a fully inflated view, which would reduce the you know, the time on the ground. And you can network this, of course, with the data into a digital twin and an inspection program to provide assurance that the aircraft is airworthy and ready to fly again. And that's the struggle and the you know, I'm sorry, not the struggle, but the example that we're chasing with our pursuits. So just to close, I want to share a couple of examples. Of course, we just saw the great Vortex drone. I showed you an example of an airship-based drone. But I think the focus can tend to resonate around the, the appeal and the novelty of the drones. But really, none of this is possible without this. So over the past year, we've performed several experiments with laser scanners, cameras, and infrared sensors, and compared those to classical processes that involved tactical type of efforts, where perhaps you would, tactically tap or rub or touch, trying to sense voids or defects. Scenarios where you would use flashlight and dental mirror in confined spaces, or where you would actually hand apply with a laser scanner to get results. And what we found is that the modern approach was superior in these three studies. Our highest capability approach for confined spaces, as an example, is to use a camera with artificial intelligence scanning and judging conformity on features inside the confined space, as opposed to reaching in with a flashlight and dental mirror. Our second best case was using a robot to apply a laser scanner, as opposed to having a human apply it. And our third best case out of the six was using an infrared scanner instead of touching and feeling along the surface for voids underneath the surface level that you can't physically see. So these, of course, show great developments and capability. The challenge as a MRO community going forward is how do we apply these inside of our hangars, inside of our run stations, and our factories. And that is where this technology needs to be combined, not only with training and awareness and acceptance of using this technology and artificial intelligence, but also how do you deploy it in terms of the robotics, whether it's fixed or flexible capital. And those are the choices that we have to make. Now, the future is very bright, of course, with aerial drones and with the Vortex producing drones and every other variant of drone. But of course, a good robotic system can work as well. And the other thing we need to pay attention to, as highlighted in the first picture, is that human with a camera and AI is just as good and capable as a drone with AI. There is a human labor charge associated with that, but it goes to point that even if you don't have a drone, you can still implement and do something with the AI technology arena. So thank you for the time, and look forward to any questions as part of the panel.
Thank you very much to all of you. We still have around 2 minutes. I would like still to raise a question and give the answer to anybody. And the question would be, from a regulator's perspective and centering ourselves in the MRO activity, what are the quality aspects that you believe that these techniques will generate from their standpoint? Who wants to respond?
Yeah, I'll start. I think from a regulatory perspective, a lot of the acceptance process and the qualification process that we use for flight testing and scenarios like that is already highly digital. But I think when it comes down to pilots and users taking ownership of the aircraft, it's still a very subjective and personal moment. And I think in those cases, the people who are signing off on the hardware using artificial intelligence, as an example, as opposed to something more classical, I don't think that they are fully aware of the capabilities or the intensity that goes into qualifying the AI. And so that's a huge barrier, and it always creates a standoff between promoters of AI and the people who are kind of against the wall saying, do I accept it or not? So I think there for sure has to be some communication, and I think that gets into the regulation. But strategically, we need to think about how to insert flexibility to use AI into those regulations, and of course the policies associated with how you would regulate that. So I don't think it will just happen, but it's got to happen through strategic insertion in our different bodies and specs and regulatory committees.
Does anybody also want to make a statement on these?
Maybe I can, if I can just say, I think one of the challenges for AI and robotics is the different disciplines that we have to bring together, and we have to work very closely together. The robots expertise, the drones, the sensors, and the AI, and that's a challenge. We do that in research projects and collaboratively, but that's already a challenge. But then I would just mention also the education, that not only are we developing the technology, but we also have to develop education programs which can pass this information on to the generation of technicians and researchers who will be working with this technology in the future, and it will also keep developing. So that's also important. It's a moving target for the education aspects.
Thank you. You want also to say something?
I fully agree that the standardization and the policy changing is a two-end game, meaning that the operators need convincing of that our technologies can work and the possibilities and the potential that they have. Because a lot of the methodologies that we are using are ever growing, and they change and they adapt to the specifications and the requirements that we always get. And most of them are always different. There are differences between operators also. So it's going to be a challenge in the next few years to see how the standards are going to evolve and are going to, let's say, be set in stone, with the robotics playing a pivotal role without overshadowing, as you very, very correctly said, the abilities of a human inspector with a good AI system and all of these balances that we need to find very, very soon in order not to disrupt, but at the end to evolve and use robotics for a better result.
Thank you very much, all. This concludes our session. I think it was a very fruitful session. You gave the opportunity for the audience to see how far we have gone in terms of, let's say, robotics in the MRO, but work is still to come. So thank you very much for your collaboration, for you, Chris, for having being raised from the bed sooner than the others. Thank you very much, all. Thank you very much. Thank you from the Portuguese Air Summit.
Thank you so much.
Thank you very much, everyone.
Obrigado.